share that iPad. There it is. Fabulous. I was going to say something else. Oh, yeah. So I've checked our schedule and the lectures that I have remaining for the class. And it seems that we are again ahead of schedule. I think I've thought about this quite a bit. Why are we getting ahead of schedule so much? And what I think is that typically when you teach this class, you're all in a room together. And if I say something that doesn't make any damn sense, then people, they got no qualms about raising their hand and asking me, well, what are you talking about? That doesn't seem to happen when we're doing this online. I can say whatever I want and nobody says anything. And so consequently, I think what's happening is because I'm not answering any questions, is that we're just blazing through this stuff super fast. So my plan today is, I'm gonna cover what it is that I intended to cover, and if we get done before 4:50, then by God, so be it. All right, we're just gonna stop. Okay, so that's the plan, and that's probably how it's gonna be for the rest of the quarter. Because again, as I said, we're running short on material here, folks, and we'll see how it goes. All right, so yeah, okay, so we were talking about magnets. All right, so we're trying to explain why are magnets magnets. And long story short, magnets are magnets because they're made out of little magnets. All right, so we're trying to explain the magnetization of materials using the Ising model. Okay, and the Ising model is that you have an array of particles, whatever they are. So usually when you're talking about actual honest to God magnetism, you're interested in electrons because they're the ones that contribute the most to the magnetism. But you have an array of particles that have some spin, and as we described last lecture, if they have some spin, that means they must have a magnetic dipole moment. That is, they act like little magnets. So like I said, magnets are magnets because they're made out of magnets. It's magnets all the way down. All right, so we started to keep things simple, talking about the Ising model in one dimension. All right. So what we had drawn was a one-dimensional array, and again, we hadn't necessarily specified our boundary conditions yet. And on this one-dimensional array, we place a bunch of electrons at regularly spaced intervals, like so. That is how electrons do. Okay, and now each of these electrons has a spin. You guys know from quantum mechanics that the spin is quantized. It can either be up or down. So it can either be up or down. So when I draw the spins, they're going to look, something like this. Okay, very good. And we are going to label each site on this lattice by an index. So the index we call I. So this is I equals 1. This is I equals 2. I equals 3, yada, 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 all the way up to I equals n. So we have n electrons. With each of these n electrons, we associate a variable that describes the orientation of that particle's magnetic moment or spin. So I think this is one thing I forgot to explicitly say last lecture. All right, so we're identifying with each electron this variable that we call sigma I that describes the orientation of the spin or the magnetic moment. It doesn't really matter which. So this variable is defined such that if the spin is up or the magnetic dipole moment is up, then it's equal to +1. So whoops, let's do this in such a way that we do it. So this is sigma 1, and that is +1. This is sigma 2, that's +1. This is sigma 3, that's -1, so on and so forth. All right, so now the thing that I forgot to say last time is that, again, when we calculate potential energies, so we said that the potential energy of a magnetic dipole in an external magnetic field was equal to this, right? Minus mu dot B. Okay, now the thing that I did not say explicitly last time was, so I did talk about how the spin and the magnetic dipole moment are coupled to one another. So if the spin is, a vector pointing one direction, then the magnetic dipole moment of an electron is necessarily going to be in the opposite direction just because it's negatively charged. And so the one thing I didn't say that I probably should have said is that we're going to say that essentially the magnetic dipole moment vector, you can write it as the magnitude of the magnetic dipole times this sigma variable. All right, and then the sigma variable just tells you what direction it's pointing in. It's either up or down. Okay, so last time when I wrote things like, well, so I'll write it down here in a second, and you'll see why this is important. Okay, so now what we were trying to do when we left off last time was to write down the Hamiltonian of this system. In particular, the Hamiltonian when we take this array and we put it into an external magnetic field. So we're also applying an external magnetic field that we call B. Okay, and so again, we write down the Hamiltonian for this, and as we came up with last time, the Hamiltonian is this. Let me just write it down, and then we can talk about it. Okay, so we said it's minus sum over all ij of jij sigma j minus mu b sum over sigma I, like so. Okay, now this term in particular is where I realized going over today's notes that I didn't say things maybe necessarily as explicitly as I should have, right? So this term, when you start, before we get it down to this format, the way we started with this term was it should look something like this, right? It's mu I dot B, right? So from this, the potential energy of each electron in this magnetic field should be its magnetic dipole moment dotted into whatever the external magnetic field is. Okay, and now, like I said, last time I neglected to say this, right? So we're assuming that you can express the magnetic dipole moment vector as just the magnitude of the magnetic dipole vector times sigma, which tells you its direction. Okay, so when you do that, that makes this equal to minus mu sum over I sigma I dot B, like so. Now, we're going to, again, it's not assume so much as this is just the way it works, that the spin is quantized, so it can either be up or down. And if our system is designed like this, that means that the spin can either be parallel or anti-parallel with the applied external field. All right, so when we do this dot product between sigma I and B, we're going to get either, plus 1 times B or minus 1 times B, depending upon the orientation of sigma I. All right, so in other words, that is why when you do this dot product, you can just pull the magnitude of B out, and then all you're left with is just summing over whether or not sigma I is plus or minus. All right, so I think that hopefully explain things there in sufficient detail that you can see how we went from this to this. All right. Okay, so now let me write it again here where everything is nice and neat so we can talk about it in more detail. Ij sigma j minus mu b sum over I sigma I. Okay, so we just talked about this term. Now let's talk about the other term. All right, so where this term is coming from is, again, it's the potential energy of each spin interacting with the other spins in the system, because each spin is putting off a magnetic field. And so again, where this came from is you're going to have some mu I dot mu j, or technically it should be mu I dot bj, right? And bj is, again, proportional to mu j, because that's what mu represents, is the strength of the field. And then mu, again, is dependent upon what sigma is. All right, so in other words, what I'm doing to go from here to here is I'm, again, just pulling out these mu's and b's and just writing it in terms of the sigma i's and sigma j's. And all those constants and units and so forth get absorbed into this coefficient, Jij. All right, so now let's talk about what Jij means, other than a collection of constants. All right, so Jij is, it's a matrix, right? Because for every value of I and j, you plug in whatever value of I and j you're talking about, and then that spits out some corresponding value of this coefficient, right? So this Jij is a matrix. It's like J11, J12, J13, J21, J22, so it's a matrix. Okay, and what these numbers represent are essentially the strength of the interaction between the spins. So the bigger the magnitude of this number, J, I mean, so you can just look at it and see the bigger the magnitude of this number, the more this term is going to contribute to the sum, right? So in other words, the bigger J is, the stronger the spins are interacting with one another. So the Jij is essentially, it's an interaction matrix. Okay, so now let's talk about the different possible values of J. So we have 3 possibilities for the different values of J. All right, so let's talk about what they are. So if we look at these values of Jij, there's 3 possibilities. One is they can be positive, okay? So if they are positive, that means that when you look at sigma I times sigma j, if sigma I and sigma j are both pointing in the same direction, either +1, so you get +1 times +1 is +1, or they could both be pointing down, so -1 times -1 is +1. Okay, so as long as these are both pointing in the same direction, you get a positive number. You get +1. You get +1. Okay, and then if Jij is positive, when you multiply Jij times sigma I, sigma j, that comes out to be positive. And then you got this minus sign out front, which flips the whole thing negative and therefore makes the energy negative. It's lower, all right? So in other words, if Jij is positive, what that's doing is it is making 2 spins that are pointing in the same direction more energetically favorable. That is lower energy states. Okay, so Jij positive favors aligned spins. It likes it. It makes the energy lower when the spins are both pointing in the same direction. If they're pointing in opposite directions, then when you multiply these 2 things together, you get -1. And then -1, again, times this negative sign out front gives you positive energy, and ooh, that's bad. Nature don't like positive energy. Okay, so if Jij is positive, that favors aligned spins, and this corresponds to a type of material that is called ferromagnetic. So ferromagnetic materials are ones where the spins typically like to be aligned, and therefore that corresponds to values of this interaction parameter that are positive. Okay. The next possibility is that Jij is negative. And now that does exactly the opposite thing, right? So if Jij is negative, then again, when you look at this sigma I dot times sigma j, if the 2 spins are parallel, then regardless of whether they're up or down, when you multiply them together, you get positive 1. And then if Jij is negative, it flips it to a negative number. And then you get a negative number times, again, this minus sign out front. That makes it a positive energy. Okay, so what is happening here if Jij is negative is that this favors anti-aligned spins. Okay, so if Jij is negative, that makes things like this happy, right? Oh, it's a little dance. All right, so these kinds of materials where this happens to be the case are what are referred to as anti-ferromagnetic. And they're rather exotic. I think it's rather unusual for a material to be anti-ferromagnetic. The final possibility is that Jij is equal to 0. And that means, again, if Jij is equal to 0, that means this term goes to 0. That means the spins are not interacting, so the spins don't talk to each other at all, and this is what is referred to as a boring material, because it doesn't do anything, so who cares? It's stupid, it's boring. Okay, all right. Okay, so those are the 3 possibilities for Jij. Now, let's talk about this again. So again, let me write it down. I just can't get enough of writing this down. Jij, sigma I, sigma j, minus mu b, sum over sigma I. Okay, now let's talk about this sum. So what is that sum? So again, what we're doing there is summing over all pairs of I and j. And the reason for that is, okay, let's assume I, for example, is equal to 1. All right, then what's happening, the way you should imagine this is that if I is equal to 1, I shouldn't use purple, I should use blue. Then, you know, it puts out a magnetic field. Oh, and now you can see, oh, spin 2 is interacting with spin 1's magnetic field, and therefore that term should contribute to the sum. But we know that, you know, the magnetic field for a dipole, I believe it falls off as 1 over r cubed, I believe, for a dipole. And that means that the magnetic field from each of these spins has infinite spatial extent. So it goes on forever. So in principle, this sum here, this sum, should be over all pairs ij. So this should be over all ij pairs. Okay, and of course you're going to do it in such a way that you avoid double counting. So you wouldn't, so if you do ij, you shouldn't do the corresponding ji. So if sigma I is 1 and sigma j is 2, then you shouldn't also do 2, 1, right? Because they're the same thing. You don't want to double count your states. But in principle, you should sum over all possible interactions between all existing spins. That makes this essentially impossible to do. You're screwed. You can't do it, right? Because that sum is over all pairs regardless of how far apart they are. So it's essentially an infinite sum, right? So it's not really analytically tractable. Okay, so what we're going to do is we're going to simplify things. So instead of doing this where we sum over all pairs, so instead we will only sum over nearest neighbors. All right, so for example, when I'm talking about spin 2, okay, then when I think about spin 2, I only need to worry about the interaction between spin 1 and spin 3, but I do not have to worry about anything any further from that, right? So I only sum over nearest neighbors. Okay, so only sum, and the way that we're going to indicate that, oh, let me write it out again. I just love it so much. Jij, sigma I, sigma j, minus mu b, sigma I. Okay, so the way we're going to indicate that is, again, we sum over all ij, But the way that we indicate that we are only summing over nearest neighbors is we put little pointy brackets around the I and j. So the pointy brackets should indicate for you nearest neighbors only. All right, sound reasonable? Sehr gut. All right, so now, in other words, if I were to write out this sum explicitly, what I would get is something that looks like this. I would get that this thing is equal to minus j1, 2, sigma 1, sigma 2, minus j 2, 3, sigma 2, sigma 3, minus j 3, 4, sigma 3, sigma 4, so on and so forth. Okay, and so you can see that, for example, spin 1, right here, its only nearest neighbor is spin 2. So it only shows up in this sum, or in that term. Spin 2, its nearest neighbors are spin 1 and spin 3. So spin 2 shows up in this term and in this term, but no others, right? And so each, again, depending upon your boundary conditions, each spin is only going to show up in one or two terms, depending on the boundary conditions, because we're only doing nearest neighbors. And of course, we're still also going to have this guy, which I didn't write. We're still going to sum over them. Okay. All right. So that's the deal. Okay. Now we have to talk about what states are available to us. Okay. So here, what I drew. Oh, it's gotten awful damn messy. Let's see if I can clean this up a little bit without destroying the whole damn. Ah, crap. Can I undo that? Oh, look at me. I undid it. There we go. And there we go. And there. Ah, ooh, fantastic. All right, so here you can see that what I drew was sigma 1 is up, sigma 2 is up, sigma 3 is down, sigma 4 is up, so on and so forth. That is one possible state for this system. Another possible state would be where everything is exactly the same except spin 1 is down, right? So in other words, the available states to this system are essentially all possible combinations of the sigmas being plus or minus. Okay, so each state corresponds to some collection of sigma i's. All right, so the way I'm going to indicate, so this is what's referred to as a spin configuration. So each possible collection of sigma i's is a spin configuration, and I'm going to indicate the collection of spin configurations by this. So it's just, whoops. So again, usually the little curly brackets indicate a set, right? So here I'm talking about the set of all possible collections of sigma 1 through sigma n, which I can write in shorthand as just this. All right, so sigma I within my curly brackets represents the set of all possible spin configurations. All right, so we're cool so far? Excellent. Okay, then guess what I'm going to do next? I'm going to write the damn thing again. All right, here it is again. H is equal to minus I, J, Jij, sigma I, sigma j, minus mu b, sigma I. Okay, now, so that is our Hamiltonian. Okay, and now we've talked about what that means. And so now we're prepared to take the next step together, right? So the next step together is we take this Hamiltonian and we start sticking into some exponentials in order to calculate a partition function. So now let's use this Hamiltonian to calculate our partition function. Okay, and so again, the number of spins is fixed. So the natural system to work in here is the canonical ensemble. And hence the Boltzmann weight we're going to use is just e to the minus beta times the Hamiltonian. Okay, so our partition function, which corresponds to having n spins, as you will see, is a function of the applied external magnetic field. That's coming from right here. And it's also a function of the applied temperature. That's coming from the beta in the exponential, right? And so the way that we can write this is, let me give myself plenty of space. It's just e to the minus beta h, where h is our Hamiltonian. And when we do this, we have to essentially consider all possible spin configurations, all right? So the way we do this is we just sum over all possible values of each of these spins. Sigma 3, sigma 2, sigma 1. Okay, so for each spin in this spin configuration, you have to sum over all of its possible values. So here, this would sum over sigma 1 is plus or minus 1. This one would sum over sigma 2 is plus or minus 1. And then you do this for every single damn spin in the lattice. Okay, so let me, now we have this, so now let me write it out super explicitly. Sum over all values of sigma 1, sum over all values of sigma 2, sum over all values of sigma 3, up to sum over all values of sigma n. And this is the exponential of, okay, now again, we got a minus sign here in the Boltzmann weight. I got a minus sign here and here in my Hamiltonian. So when I distribute this minus sign from the weight in, everything comes out to be positive. And so I get exponential of beta sum over nearest neighbors jij sigma I sigma j plus beta mu b. Oh, that's going to get confusing, isn't it? Sum over all spins there. So that is our partition function. Okay, so it looks kind of like a mess. All right, so now we're going to make one more simple assumption, and that is all of our spins are more or less identical. Okay, so they're all electrons, they're all equally spaced. In other words, the magnitudes of this jij are going to be the same for every possible interaction. Okay, so let's assume that all jij are just equal to the same value, which I'm going to call j. Piece of cake. Okay, so our partition function is again function of b and t, sigma 1, sigma 2, sigma 3, sigma n, exponential, beta j, sum over ij, nearest neighbors, sigma I, sigma j, plus beta mu b, sum over all I. All right, there it is. Okay, and so that is the partition function. Once we have the partition function, then we'll calculate the free energy. And the free energy is just minus inverse beta log z. Right, so and then once we have the free energy, then we just start taking derivatives in order to calculate expectation values. Okay, so this is what we're going to spend the next several days talking about. Okay, now, again, what it is we're trying to explain here is magnets. All right, and so now the average that we're going to want to calculate from this thing is what is referred to as the magnetization. All right, so from this, and by this I mean the partition function and the free energy. So from this, we want to calculate what's called the magnetization. All right, so the magnetization, very simply, so we call that capital M, and because the partition function and the free energy are functions of B and T, this is also going to be a function of B and T, so it's a function of the applied external field and the temperature. What this is simply the average magnetic dipole moment over all spins. That's it, piece of cake. Okay, now the average dipole moment, again, we said that we were going to write this vector mu as equal to the magnitude of mu times our little spin variable. And so now this we're going to write, it is just equal to mu because it's a constant. You can just pull it out of the average. And so this is mu summed over all sigma I. So in other words, what we want to do is for each location on the lattice, we want to calculate its average orientation. Well, we want to add up all of the spin variables and then average over all of those possible spin configurations. So this is our goal, is to calculate this thing. Okay, so how are we going to do that? So again, in StatMech, what you do is you write down your partition function, okay? Then you look at the thing that you want to calculate. Okay, so I want to take the average of the sum of the sigma i's, right? So now you go back to your partition function and you look for something that is multiplying the thing that you want to take the average. Look, here it is. So this right here is the thing that I want to take the average of. Then you look for some parameter that is multiplying that thing that you want to take the average of. So I got a few choices here. What I'm going to do is take B, all right? Because you can see that B is unique to this term, okay? Beta is in both of these terms. So if I differentiate with respect to beta, then I'm going to get some contribution from this term too. No, I don't want to do that. I only want this sum over sigma i's. So the thing that I'm going to choose to differentiate with respect to is B, because that when I differentiate with respect to B, that'll pull down this factor of sum over sigma i's, and that'll therefore give me the expectation value of the sigma i's. Okay, so in other words, the magnetization, once you have the free energy, you just differentiate the free energy with respect to the magnetic field. Okay, when you differentiate the free energy with respect to magnetic field, that'll pull down this factor of sum over sigma i's, and then that is your expectation value. All right, so that's what we want to do. We calculate our free energy, differentiate with respect to the magnetic field, that gives us the magnetization. Okay, straightforward enough. Now, magnetization, that's what we're after. In particular, we are interested in this magnetization at 0 external magnetic field. All right, because you guys have played with magnets before, right? You take something like a frog, for example. You can find videos of this on YouTube. You take a frog, you stick it in a magnetic field that's strong enough, that frog is going to become magnetic. It's going to start floating around in space, affected by the magnetic field. It's ridiculous. I highly encourage you to go look this up on YouTube when we're done here. Anything, you put it in a strong enough magnetic field, it's going to act like a magnet. All right. So if you get a magnetization with an applied external magnetic field, yeah, you know, that's to be expected. That's just the way things work, right? What's really interesting is when you have a net non-zero magnetization with no applied external field. So that's what we call a bar magnet, right? So a bar magnet is a hunk of material that even when there's no external magnetic fields around, it still has a magnetization. So this value of the magnetization when the applied external field is equal to 0, this is what's referred to as the spontaneous Magnetization, spontaneous magnetization. Okay, so this is really what we're interested in. Okay, and so now if there is no net external magnetic field, if there is a spontaneous magnetization, that has to come from just the interactions of the spins themselves, right? If we look at our Hamiltonian, so we look at our Hamiltonian, if B here, if B is 0, that means that we can only get alignment or anti-alignment of our spins as a result of the spin-spin interactions. Okay, now, okay, so in other words, what we got is two spins that are interacting with one another. And now this is also a function of the temperature, right? So that we also have to include temperature. And what temperature does in statistical systems like this is it introduces fluctuations, right? So the higher the temperature, so say we got two spins like this, they're going to be, if there's a temperature, they're just going to spontaneously be fluctuating. And the higher the temperature, the more fluctuations you get, okay? So now what we expect is that if the temperature is very high, the fluctuations from the temperature are going to be very large, and they are essentially going to overwhelm the spin-spin interactions. In other words, the strength of the spin-spin interactions are going to be insufficient to keep the spins aligned if the temperature is high enough, right? Because the thermal energy just makes them want to jiggle. Okay, so what we expect is that at high temperature, there should be no magnetization. T large. This should average out to 0. So again, we're just going to essentially have random fluctuations. And when we average over the random fluctuations, everything just averages out to 0. Now at low temperature, okay, again, low temperature corresponds to not so much thermal energy. And so then the interactions between the spins are going to be dominated by these spin-spin magnetic field interactions. And therefore, you know, depending upon the value of J, they're either going to like to be generally aligned or anti-aligned. All right, so at low temperature, we expect the the strength of the spin-spin interaction to overcome the thermal fluctuations, and therefore you would expect the magnetization to be non-zero. Okay, so high temperature, no magnetization. We expect at low temperature, we will have a magnetization. That implies that something interesting is happening between these two regimes. That implies that somewhere there is a critical temperature. This is called, I believe, the Curie temperature. Okay, so there's a critical temperature that if you're above that critical temperature, you got no spontaneous magnetization. And once you hit that critical temperature and go below, you do get spontaneous magnetization. And so this is what is referred to by physicists like ourselves as a phase change, right? Okay, so the two phases we're talking about are unaligned spins at high temperature. It's just like freezing water, right? So at above 0 degrees Celsius, you've got randomly oriented water molecules, and you get water. Okay, you hit the freezing temperature and everything just spontaneously aligns and they freeze together and they change phase. They go into, they become ice. So you change phase from liquid water to solid water, ice. So it's exactly the same thing going on here, that above this critical temperature, the spins are all just randomly oriented from thermal fluctuations. As the temperature goes down, those thermal fluctuations get less and less, and then at some critical temperature, bam, they freeze and you get some spontaneous magnetization. Okay, does that make sense? So what we're looking at here, what we're going to ultimately be talking about is the statistical mechanics of phase changes. Now there's a complication. Okay, So what's the complication? The complication is, so we're going to work through the Ising model. And the thing about the Ising model is that in one dimension, you can show rigorously that there are no phase changes. In 1D, there are no phase changes. So in other words, the one-dimensional Ising model is not adequate to explain the onset of spontaneous magnetization. We're going to work through it anyway, just to see how it behaves, and then we'll talk about what happens when you go to higher dimensions. Now, it turns out that in 2D, and the reason we're going to do it in 1D, again, so 1D, we're going to do 1D, and the reason we're going to do it is because it is easy. Okay. Then the next highest thing you can do is 2 dimensions, right? So now you might ask, well, how does the thing behave in 2 dimensions? Okay, so 1 dimension is easy. You might imagine that 2 dimensions is maybe not that much harder. You would be wrong. All right, so it turns out that once you go from 1 dimension to 2 dimensions, it becomes much, much, much more difficult. However, it is still tractable. You can still do it. So in 2D, it's still tractable. And you can show, in fact, that in 2 dimensions, you do get phase changes. Okay, we're not going to do it because it's really hard. And in fact, the fella who did this, his name was Lars Onsauger, I believe. He is, we're posting this on YouTube now, so I don't want to say anything that could potentially be offensive, but he was like a human adding machine, right? He's the kind of guy that made Paul Dirac look like a gadabout town, right? He was into this. So Lars Onsauger showed that you could do this like somewhere around the early 1900s, and I believe he got the Nobel Prize for showing that you could do this in 2D. So it's really hard. It's hard enough that if you do it, you get a Nobel Prize. And then you say, what happens in 3 dimensions? And the answer is we still don't know. So presumably you're still going to get phase changes, but it turns out that once you go to 3D, that's when you're talking about, ultra galaxy mind kind of type person is the only people who can solve this, right? So this still has not been done. I don't believe it's rigorously been shown exactly what happens in 3 dimensions. So, again, if you can show it, I'll buy you a Coke. Okay, so what we're going to focus on is, okay, that's delightful. You see, I have it on Do Not Disturb, and yet we still got disturbed. Come on, Apple. Get your stuff together. So what we're going to do is we're going to work through the Ising model explicitly in 1 dimension. We're going to talk about qualitatively what happens in 2 dimensions, and then we're just going to forget about the fact that 3 dimensions even exist, okay? So we're gonna do 1D, we're gonna talk about 2D, we're gonna talk about how to understand phase changes in 2D, and yeah, that's where we'll come to a stop. Okay, so let's do it in 1 dimension. And we're gonna work through this thing in painful, excruciating detail. Somebody's got something to say? Chat. 2D is the best dimension, you betcha. All right, so now when we're going to work through it in 1D, but even in 1D, it's still not trivial. All right, so we actually have 3 cases that we're going to work through explicitly in 1 dimension. The first one we're going to do is what's called the non-interacting model. Okay, and the non-interacting model is when J is equal to 0. As the name implies, the spins don't interact. They only interact with the applied external magnetic field, and we'll see what happens in that case. The next thing we're going to do is the zero field model. And that is when the spins are interacting, but there is no applied external field. And we'll see what happens. In fact, we'll see that essentially what happens is you get the same result in both cases. And then the final thing we're going to do is the general model. And that is when both B and J are not equal to 0, and it gets a little hairy. In fact, I don't think it's analytically, you can't get, I believe, a closed analytic form for what or at least we're not going to do it. We're going to work through and see essentially how the thing behaves. I'm going to plot for you what the solutions look like and to get a feel for how the thing behaves, but I don't think we're going to write down like a closed form, this is the answer type of thing, because even at this point, it still gets pretty complex. And then we're going to talk about phase changes in 2 dimensions and higher. Okay, so now we got 2 options. We can start doing the non-interacting model, or we can stop. And I see, looking at the clock here on my computer, it is now 4:48 p.m. Just changed to 4:48 p.m. I think we might as well call it quits here. Does that sound reasonable to you guys? Nobody ever says anything. So we'll assume that you're in. Oh, we got a bunch of thumbs up. Fabulous. And somebody even put something in the chat window. What are you saying? Yeet. I don't know that that's proper use of the word yeet, young man. My understanding of yeet is that it's the opposite of yoink, right? Yoink is when you pick something up. Yeet is when you chuck it across the room. So we're going to call it quits here. Again, no class on Monday. So I'll see you guys on Wednesday. And now is the point where I'm supposed to ask you, do you have any questions? Do you have any questions? You don't. All right. So we're done. I'll see you guys next Wednesday. Yeet. Oh, I shouldn't have said that till I was ready. The end button, because now I look stupid.